audible. If there is any disturbance in the audio, please let me know. And if there are any doubts from any of the previous live sessions or any of the previous week lectures, you can post it in the chat box, and I'll try to discuss those. So, week 5 course content was mostly focused on microbial growth kinetics, monod kinetics, transient growth kinetics, primary and secondary metabolites. So this was the main theme. So until this week, we have seen about enzymes, enzyme inhibition, enzyme kinetics, and inhibition kinetics. So now, we will see about microbial growth kinetics. So whatever we saw as Michaelis Menten, here we applied as a monod kinetics, and the primary understanding is that a microbe is a group of enzymes working together. So in enzyme kinetics, it's about the individual enzyme. Again, microbes are systems in which numerous enzymes together work as a system. So we try to translate our models to the microbial growth as well. So with that introduction, until last week we had solved many problems, because it was concepts where we try to solve some lengthy problems. So this week, maybe depending on the course content as well, we will try to solve some non-numerical questions. So there are mostly non-numerical questions, but we do have few problems at the end of the session. So we'll first start solving the questions. The first part would be assertion and reason questions. Like always, I'll just wait for some time for you to answer, and then we can discuss. So the first question is, a culture can show a measurable increase in turbidity even when the number of viable cells is decreasing. Turbidity detects suspended particles and does not necessarily distinguish living cells from dead cells or cellular debris. Liquid culture, we go for optical density or turbidity based measurements, and in these measurements what actually happens is we pass on some light, and we are trying to capture the light scattering. So when there is going to be some particles suspended in the solution itself, we are going to get a reading in those measurements, but we cannot conclude whether these particles are live or dead, are they even cells or any other particle that's being suspended, any kind of contamination. So we will not know what kind of suspended particles they are. So a culture can show a measurable increase in turbidity even when the number of viable cells is declining. Similarly, turbidity does not distinguish live cells from cellular debris, and that's why we go for some culturing techniques. Okay, so the next question is, a high substrate concentration always produces the maximum possible specific growth rate. The reason is that suppose the assertion is that in the monod model, increasing substrate concentration raises the growth rate towards mu naught. what happens is at high substrate concentration, uh, it is n- it is not necessary that always your maximum specific growth rate is achieved, because at very high concentration you can experience something like substrate inhibition, like where you have excess of substrate, that again becomes inhibitory to your bioprocess. So at high substrate concentration does not always produce the maximum specific growth rate. At excessively high concentration, sometimes many of the substrate exhibit a phenomenon called substrate inhibition. And when there is substrate inhibition, you know that the uh, growth rate will decrease. So it's not a direct correlation and it's not happening always. So that's why the reason is false. Sorry, that's why the assertion is false. But speaking about the reason, we know that the monod kinetics talks about mu is equal to mu max S by Ks plus S. So when we are going to increase the substrate concentration, the mu max is going to increase towards the mu is going to increase towards reaching the mu max. Uh, Based on the equation itself, we can tell that whenever substrate concentration is increasing, your specific growth rate will increase such that it is going to reach your maximum specific growth rate. The first statement, which is the assertion, is not always right, because we have studied about a phenomenon called substrate inhibition. I hope it is clear. There is anything more to be discussed, you can let me know about this question. The next question is, a low Ks organism is generally advantageous when the limiting substrate is present at a low concentration. Reason is, a low Ks indicates that the organism can achieve a relatively high fraction of mu max at low substrate concentration. I mean, the mu max is repeated, it's just one. The reason is, a low Ks indicates that the organism can achieve a relatively high fraction of mu max at low substrate concentration. Okay, so yes, both the assertion and reason are true, and the reason correctly explains the assertion. So first we will break down what the assertion and the reason says. So in our assertion, the statement says that a low Ks organism is generally advantageous when the limiting substrate is present at a low concentration. So here, first of all, Ks is the term in the monod equation which represents the half saturation constant. So what is a half half saturation constant. It is the substrate concentration at which the specific growth rate is half of mu max. It is whenever mu is equal to mu max by 2, the substrate concentration is called Ks, and it is an indicator for the substrate affinity of the microorganism. If the Ks value is low, then the organism has a higher affinity towards the substrate. So when we talk about a situation called limiting substrate, it means that this substrate is present at a very low concentration compared to other substances in the media. So at low Ks, that means when the organism is having a higher affinity, it can grow efficiently and it can achieve the significant fraction of the mu max. So what happens is, this gives, like when we talk about a mixed culture or something, this gives the organism with the low Ks a advantage over other organisms to efficiently survive in the given environment. So that is why this assertion is true. The reason is, at low Ks indicates that the organism can achieve a relatively high fraction of mu max at a low substrate concentration. This is like when we talk about the monad kinetics, it is mu is equal to mu max S by Ks plus S. Here what is given is low Ks, which is Ks very less than S. If we are going to substitute this condition in our equation, it means that mu is equal to mu max. So let's say if Ks is very small than S, then your denominator in the monad kinetics is approximately going to be equal to your substrate, and the S by Ks plus S term will be approaching 1, which means that our mu is approximately equal to our mu max. So because a low Ks is going to allow the organism to grow at a specific growth rate, which is very nearer to its mu max value. So that is the relationship between the affinity of the microorganism with the substrate and its growth rate. So based on the kinetic equation, we can tell that at low Ks, mu is going to approach mu max very closely. So in that case, both assertion and the reason are right. And here we talk about how the substrate affinity works and how it correlates with your specific growth rate. So both the reason correctly explains how the assertion works. So that is why both assertion and reason are true, and the reason correctly explains the assertion. Okay, so the next question, the assertion states that the Malthus model is unsuitable for predicting the entire growth curve of a batch culture. The reason is that what they say is the Malthus model assumes exponential growth and does not account for nutrient depletion or growth inhibition at high biomass concentration. here when we talk about the Malthus model, it says that the population at a given time t will be equal to the population at time 0, which is the starting population, into e power rt, where r is the growth rate and t is the time. So we have this term called e power rt in the Malthus equation, which says that there is going to be exponential growth. And here we only have two factors. One is the rate and next one is the time. And given with a given rate and for a given time, there will be an exponential growth of a microbial population from the initial population, is what is the Malthus model says us. But before saying that, for any model we have to know about where the model is suitable or under which conditions we can use this model. So when we talk about Malthus model, in that case, here it assumes that there is unlimited substrate or nutrient or food available for the microorganism. There is no competition for space. There is no change in the environmental conditions. So food, space and environment, all of it is going to be abundant. That is what is the assumption of Malthus model, to say that the population increase is going to be exponential. So keeping that in mind, our assertion says that Malthus model is unsuitable for predicting entire growth curve of a batch culture. It is true, because what it assumes is abundant substrate and abundant space and no change in environmental conditions. But when we talk about batch culture, we are not continuously feeding it substrate. So what happens is, at one point there is going to be substrate depletion, and the environmental condition is not also going to be staying the same, because there can be changes due to accumulation of the products in the system as well. So basically this system does not work well with the assumptions of the Malthus model. So we cannot use a Malthus model for predicting the entire growth curve of a batch culture. Again, talking about the reason, Malthus model assumes exponential growth, that we saw, and does not account for nutrient depletion or growth inhibition at high biomass concentration. So that is what we have discussed so far on the assumptions, as well as what is the model that Malthus proposed. So both are true, the assertion and reason are true, and the reason is a correct explanation for the assertion. So you may have doubt then, why do we even have Malthus model, where it is used? So it is used to model a model to find the maximum specific growth rate, or to predict harvesting timelines. So to calculate the doubling times, or when we are going to start a reactor, we need to do some preliminary analysis. So in these analysis, you can use the Malthus model, and you need to prepare a large amount of inoculum. So what you do, you just apply it with enough of substrate, and you do this inoculum harvesting before you can start a proper bioreactor. So all this basic stuff, we can use Malthus model for doing these. But again, predicting a entire batch culture growth is not gonna work out. The next question is, the assertion states that during the stationary phase, the specific growth rate must be negative. The reason is, in the stationary phase, the number of cells produced is approximately equal to the number of cells lost. decline phase majorly. So when we talk about the lag phase, we have the growth rate is 0 because there is no increase in the cell number. When we talk about the exponential phase, it's going to have a high positive growth rate uh, because the cells are actively dividing. And when we come to the stationary phase, the specific growth rate is not negative but it is 0. Why? Because the reason correctly explains that what is a stationary phase. In stationary phase, the number of cells produced is approximately equal to the number of cells lost, because there is going to be this substrate depletion starting. So there is going to be substrate scarcity, and also simultaneously toxic waste buildup is also going to be there. So at one rate there can be, without whatever the substrate is available, some cells may divide and produce new cells. On the other hand, some other cells which are starving without the substrate are going to start to die. So both these will happen parallelly. So the net specific growth rate is going to be 0. Here the specific growth rate is not negative but it is 0. So that's why the assertion is false but the reason is true. Okay, so with that we have completed all the assertion and reasoning. So I have questions from different, like I told, problems are in the last section. Then we have fill in the blanks, some match the following questions to discuss all the concepts. So the next question is, if the specific growth rate is reduced by nutrient limitation but cells remain viable, the culture is most likely in what phase rather than the death phase? Just now we saw the answer. Okay, stationary or a declining phase but not essentially the death phase. So I hope you understand the difference, because the small curve after the stationary phase and before the death phase is something what I mentioned as decline phase. So in that particular zone, the growth rate is reduced by nutrient limitation but cells remain viable. It's not like they are completely dead. Okay, so the next question is, in a model that treats all cells as having identical average properties but explicitly represents intracellular components, the model is structured and dash. You have to just fill in the blank. population models, we can classify those into structured, unstructured, segregated and unsegregated models. So when we talk about an structured model, in structured model it explicitly considers all the cellular components like RNA, DNA, proteins, metabolites, all of it are considered while modeling, and that is like the entire structure of the cell is considered. That's a structured model. When we talk about an unstructured model, it those models treat cell as one single unit with a fixed composition. It does not account for any other intercellular or intracellular variations uh, that could affect the model predictions of a particular system. On the other hand, when we talk about segregated and unsegregated models, segregated models recognize that individual cells in a population differ from one another, but unsegregated model assumes all cells have identical properties. So here we are given that a model treats cells as having identical average properties, but explicitly represents intracellular components. So because it explicitly represents intracellular components, you call it a structured model. Since it treats all cells as having identical average properties, you classify it as an unsegregated model. So the specific growth rate increases from zero point 0.2 to zero point 0.4 per hour. What is the effect on generation time? at which something is happening is increasing, then obviously the duration is going to become lower. So basic answer is it is going to become shorter. But mathematically, when you are going to use the equation for this, which is your generation is equal to ln 2 by mu, and your mu is in the denominator, right? So what happens, whenever your mu is going to become high, your g is going to become low, because they are inversely proportional, as you have told. In this case, what happens exactly is it's going to double. So this factor is going to become 2x. In that case, it will completely become half of it. The basic answer is it will become shorter. So at least that you have to know. But exactly what happens is it will become half of it, because that's how the inverse relation works. Okay, those were few questions. Now you can try to match. We'll start with a simple question. So you can just give like A1, B2, C3, D4 in the chat box. So we have seen this in one of the previous questions where we talked about stationary phase. We have different growth phases when we plot a microbial growth curve. So ideally the first phase is the lag phase. As the name suggests, it's in when we plot about the number of cells and the growth rate, when we talk about it, is a lagging phase where nothing in terms of number moves. The number stays constant because it's just a cell getting adapted to the environment that it is being introduced to. It's trying to build its internal system to match and grow in the given environment. So it's a physiological adaptive phase. That's why A pairs with 2. When we talk about the log phase, in log phase we have maximum active multiplication. That's why we call it a lag or exponential phase, where we tell that the growth is in exponential or a logarithmic way. It's not even linear. It just multiplies in a exponential. The number gets multiplied in an exponential phase. So that's a maximum active multiplication phase. When we talk about stationary phase, it is zero net population increase. I think I don't want to repeat because it's the same that we saw there. Number of cells forming is equal to number of cells getting lost in the system. So that is stationary phase. And in the death phase, the decline takes over. So in the log phase, the increase is taking over, but in the death phase, the decrease is going to take over. So here you see a net loss of viable cells. Your loss is going to be very prominently seen here. So these are the 4 phases of microbial growth kinetics. You have to pair up the product with its application. one is ethanol as a fuel or beverage. So we all know about this ethanol blended petrol stuff that is happening, or ethanol being used as fuel. All this we all know. So ethanol as a fuel and ethanol as a beverage, where it's a primary thing in breweries. So ethanol as fuel or beverage, even if one of the options is given, we'll directly match it. And when we talk about riboflavin, vitamin B2, what we call as vitamin B2 is actually riboflavin. So, and it's a micronutrient. Similarly, when we talk about amino acids and enzymes, there are two more options: flavor enhancers and detergent and food applications. In amino acids, I guess when we talk about products, one product which is glutamic acid is an amino acid which is very famous, and we all know that monosodium glutamate, MSG, or the common commercial name that we know that with, all that is generally attributed to flavor enhancing in food. So amino acids, when we talk about, mainly if you even keep the example of glutamic acid or monosodium glutamate in mind, then it's a very good flavor enhancer. And similarly, when we talk about enzymes, food applications is fine because we know that in baking, brewing, all these industries come under food industries. So in all these industries, we use different enzymes. But when we talk about detergents, we use again enzymes to break down stains. So we all have different kinds of stains. We all know different places where we could potentially get our clothes stained. If this stain could be removed by the enzymes that could break it, like proteases, lipases, which can break down proteins and uh, lipids or oil. So in that case, enzymes are also used in detergent uh, making, as well as food application is, yeah, commonly known. So ethanol goes with fuel or beverage, vitamin with riboflavin, amino acid is a flavor enhancer, and enzymes as in detergent and food applications. Okay, match the models with their assumptions. Malthus model. So in Malthus model, just now we saw that it assumes exponential growth because it conveys that there is exponential growth in the microbial population because it assumes that the substrate is unlimited, the population is not being disturbed by any environmental interferences and all. So this is, as we saw, it's the simplest model where it assumes that there is going to be exponential growth of microbes. So it is dx by dt is equal to mu x, which means that there is going to be exponential growth in the system. Next is the logistic model. So the logistic model equations says that dx by dt is equal to mu max x into 1 minus x by k. So here we all know that the growth in population is going to depend on the initial biomass concentration, the growth rate, and there is one more factor that's getting added in this model, which is the carrying capacity. What Malthus model told was the microbe can grow in infinite numbers, but in real space scenario, for a given reactor, there is a confined space in which the microbes can grow, and there is a confined amount of substrate that will be given to the microbe. So there are limitations. If the microbe is going to exceed that maximum ceiling window, then it cannot grow. So at that time, you cannot expect the exponential growth to happen. This factor is what is termed as carrying capacity in the logistic model. So as the microbial growth approaches the carrying capacity, the growth starts to decline. When we talk about monad model, we all know that it has a substrate term involved in it. So growth does not only depend on the microbe itself. So until now we saw that it depends on just the initial number of microorganisms and the growth rate. But there is a way. So in the second model, they introduced a factor called a K factor, which is the carrying capacity. And now in the next model, what happens is they tell that not only the microbial population decides the growth, it's also the substrate available that that decides the growth of the microorganism. So here they include a term of S, and the equation goes to be mu is equal to mu max S by Ks plus S. And in the next model, which is the quantized model, what happens is, even if there is enough substrate available, if the microbial carrying capacity is reached, I mean when a given space only this much of biomass can grow, then only that can grow. Even though if you are going to give more food, you cannot expect growth because in the particular system only this much can be occupied. So what happens is they are also taking into account the biomass that is present in the system. So when you talk about monad model, you see that growth rate is there, substrate is there, and also the affinity factor is there, but it doesn't account for how much of the microbe is there and how it can proliferate. So here they modify the monad model as mu is equal to mu max S by Kc into x plus S. So they include a term for the biomass to account for the biomass crowding. If the biomass crowd is more, again your growth rate will decrease. This is what quantized model is telling. So this is the evolution of Malthus, logistic, monad and quantized model, and the match is Malthus model says about exponential growth only occurs in a microbial system, whereas logistic model includes the biomass limitation, and the monad model includes substrate concentration, whereas the quantized model talks about the dependence on both the substrate and the biomass. Okay, this, I think we have already seen this. I'll just wait for a few minutes for you to get the answer. as we saw about the structured, unstructured, segregated and unsegregated models, in structured model it considers the internal composition of the cell like DNA, RNA and other organelles or any other intracellular component of a cell, whereas in unstructured model it doesn't like consider all these. It just says that a single cell is a single entity. It assumes the cell composition is constant. There is not going to be any variations in the cell composition. So therefore it talks about only the cell as one unit. A biomass will behave like that without any differences. So that is the difference between structured and unstructured model. So the structured model talks about intracellular components, which is true, and unstructured model talks about average cell behavior. When we talk about segregated and unsegregated model, segregated model tells that a culture consists of heterogeneous individual cells, and all these cells can have different age, different size and different metabolic state. So that is what we call as individual cell heterogeneity. Not all cells are same, even though they are all cells, even though we have a pure culture of same species, but essentially the age of the cell need not be the same. It need not be metabolically the same, or the size may differ. So all this heterogeneity is accounted in segregated model, whereas in unsegregated models, all the populations, all the individuals in a population are considered to be single uniform lumped systems. So all over the reactor system, all the biomass that are present are going to be considered as uniform lumped biomasses. So an unsegregated model pairs with single lumped cell component. Okay, another easy question. We have been seeing this anabolism, catabolism, primary, secondary, all of it for in the other week lectures and live sessions as well. So yeah. Exactly. So we all know that catabolism is breakdown of molecules in the system, whereas anabolism is building up. So anabolism pairs with synthesis of larger cellular molecules, whereas catabolism, the breakdown of the food or the complex molecules into simpler molecules along with energy generation. So when you break down, what you get is the carbon skeleton that is being generated, and this will be used for the anabolic processes to build new molecules. Similarly, you get energy in the form of ATP. And primary metabolism, we all know it is linked with the organism's growth itself. The products that are produced during active growth phase, and they are essential for the microbial growth. These are primary metabolites, and the process is called primary metabolism. And when we talk about secondary metabolism, they are specialized product. They are not produced during the active growth phase, but rather than in the stationary phase. They are not growth dependent factors, like they do not contribute to the growth of the microorganism, but still for the survival of the microorganisms they do help. They are additional metabolites, not the ones that are primarily required. Okay, this is also a recap question. We have seen about this in enzyme topic probably last week. Okay, when we talk about competitive inhibition, the inhibitor is directly going to bind to the active site where the substrate is supposed to bind. So here there is a direct competition between the inhibitor and the substrate. So here we need an increase in the substrate. So when there are 100 substrate molecules present and 50 inhibitor molecules present, the competition is going to be high. But when there is 500 substrate molecule present and only 50 inhibitor molecules, then competitively substrates are more prone or have the more probability to go and occupy the active site. So this is competitive inhibition. When we talk about non-competitive inhibition, here the inhibitor is not in any competition with the uh, active site of the enzyme, but rather it binds to an other allosteric site, and this has an tendency to happen in both free enzyme as well as in the enzyme substrate complex. So there is going to be allosteric site present in the enzyme any time. It can bind to the enzyme when it is in the free form or when it is in the enzyme substrate complex. So here what happens is it reduces the total amount of functional enzyme in the system. So the activity comes down, which is supposed to be the decrease in maximum rate, where we call it as Vmax in Michaelis-Menten kinetics. So here it has an effect on Vmax, but the Km is not going to be affected because of this. So it pairs with 1. Maximum rate is going to decrease because the available enzymes for the reaction is going to be reduced. The effective enzyme concentration is going to get reduced, but affinity, which is the Km value, is not going to be changed because it's no competition with the substrate. Substrate can go and bind to the active site as always. And when we talk about uncompetitive inhibition, apparent affinity and the maximum rate both will decrease because the an uncompetitive inhibitor goes and binds only to the enzyme substrate complex. So here what happens is it prevents the complex from completing the reaction. So ES is just an intermediate. It has to become E plus product. Uh, the binding of an uncompetitive inhibitor prevents this forming of the product and resulting in a lower reaction rate, which is a decrease in Vmax value. So what happens? There is substrate bound to the enzyme, and more substrate cannot bind to the enzyme. So here the apparent Km value or the apparent affinity is going to get affected because it directly binds only to the enzyme substrate complex. So in an uncompetitive inhibition, both apparent affinity and the maximum rate decreases. That's why we use the term apparent affinity. So intermediately in the system, when there is enzyme substrate complex already produced, ideally what should happen is it should get separated as enzyme and product. So a new substrate can come and bind to the enzyme, and this process will continue. But when an inhibitor is going to arrest the enzyme substrate complex, then all the enzymes are going to be occupied by substrate and be bound with an inhibitor. Nothing is going to progress there. So the apparent affinity will decrease and the maximum rate will also decrease. And when we talk about product inhibition, inhibition is caused by accumulated product. So what we see in stationary phase maybe, because there is more of product, the forward reaction is not going to be spontaneous anymore. In that case, you have to remove the product in order to again make this spontaneous. Sometimes the product is going to be toxic to the microorganism rather than only stopping the forward progression of the product formation reaction. It can also be toxic to the system. Let's say when acid production is happening, more acid accumulation not only gives an feedback inhibition but also plays a major role where the pH drops, and that could be detrimental to the microorganism itself. So all this is possible in the product inhibition. Okay, one more question based on growth phases, but this time based on the metabolites. Okay, when we talk about exponential phase, there is going to be active growth in the exponential phase. it. Okay. So in okay, so in trophophase, what happens is in the initial growth phase, and you can see where you can see an active growth. Here, the cells will divide rapidly and experience intensive primary metabolism. So, what you generally get a confusion is that in which stage which is found. So, in trophophase, you can see that the cells will divide rapidly, and this is kind of a primary metabolism. But when you talk about idiophase, it comes right after the active growth period, where the microbes are starting to produce secondary metabolites. So, and then when we talk about exponential phase, here this is the complete stage in which the primary metabolites are being produced. The cell synthesize essential cell components, and these components mostly are the primary metabolites that are required for the microbial growth. And when you talk about the stationary phase, here the specialized metabolites get accumulated. So the growth rate will slow down, and all the secondary metabolites which is starting to produce in the idiophase will get accumulated. So the right match is the trophophase pairs with active growth. That's the active growth phase. And idiophase goes with secondary metabolites. In exponential phase, you see the primary metabolites getting produced. Like it's a phase completely for primary metabolites, and the stationary phase, specialized metabolite accumulation happens. So I guess you just got confused with trophophase being the phase as primary metabolite production. No, in the exponential phase itself, the reason why you see an exponential growth is because all the primary metabolites like the RNA and other amino acids that are required are being continuously produced. So that's why exponential phase pairs with primary metabolites, whereas trophophase it's said to be the active growth phase. You in this you just have to match equations with whatever they are trying to incorporate in the equation. mu t is the ideal exponential growth. Here you know that the substrate is going to be abundant, and you assume a exponential growth. So that's how exponential or logarithmic phase works. The next equation is mu is equal to mu max s by ks plus s. It is the substrate limited growth, where the amount of substrate determines how the growth of the organism is going to be. And talking about the next, dx by dt is equal to mu x into 1 minus x by x max. It is the growth with the carrying capacity, where this 1 minus x by x max is the uh, factor for the carrying capacity factor. And next one is mu is equal to mu max s by ks plus s minus kd, which is where the kd tells about uh, some decline in the microbial growth, and this decline could be due to many inhibitions. So this is biomass growth with inhibition. Okay, this is about filamentous organisms. So here when we talk about pellet, we describe the physical or the morphological structure where the filamentous fungi or bacteria uh, happen to grow. And then when we talk about pellet interior, obviously there is a great diffusional limitation to the pellet interior, because the nutrient has to be in the bulk solution, then it has to uh, go through a film and then into the pellet, and then move across the pellet to reach the interior. So to for a substrate, for a nutrient or oxygen to reach the pellet interior, there is going to be high diffusional limitation. And when we talk about larger pellet, the distance of travel into the interior is going to be even higher, which is the greater transport distance, because the diameter of the pellet is going to be higher. And when we talk about mold biomass, in mold biomass, the concentration is usually represented in terms of mass per volume. How much of the mold is grown in a given volume? Mass or weight by volume is what we use. Okay, this we have seen in both Monod and Michaelis-Menten kinetics. mu is equal to mu max S by Ks plus S, or D is equal to V max S by Ks plus S. Just substitute the conditions and then you will get the match. We have also discussed this in many of the previous sessions. So in mu is equal to mu max S by Ks plus S, when the substrate is going to be very high, then the Ks term is not going to be there. I mean, it's going to be very insignificant. So your mu will be approximately equal to your mu max. So it's near mu max. And um, when we talk about S is equal to Ks, then when we talk about X is equal to Ks, we know that Ks is the substrate concentration at which there is half of mu max achieved, so it's 0.5 mu max. And when the substrate concentration is very low, then mu is equal to mu max S by Ks, because your S term is going to be very insignificant. So there is strong substrate limitation there. And when substrate itself is not there, then no growth will take place. So your mu is equal to 0. Okay. Based on the statement, you can see which of the conditions can apply to this. So they say that two organisms are grown with the same substrate concentration, where organism A has the Ks of 2 milligram per liter and B has 20 milligram per liter. Out of these two, which one will work best in? And they also say that the mu max is equal. Only difference is a Ks. organisms are having same mu max. The difference is in their Ks value. When we say there is low substrate concentration, it can be a limited substrate condition, as we saw in one of the previous questions. So when there is limited substrate, the organism A is expected to have higher growth rate. Why do you think B would have? How an organism with a lower Ks value means that it has higher affinity to the substrate, or is it vice versa? Organism A has lower Ks value compared to organism B. Isn't it that an organism with a lower Ks value indicates a higher affinity for the substrate, or is it a direct relation? Lower Ks means lower affinity. Okay, so lower case tells that there is more affinity, so which means organism A is expected to have higher growth rate at low substrate concentration because it has a higher affinity towards the substrate. B does not have that much affinity to the substrate, even though it can grow at the same rate when both of the organisms are going to have equal share of the substrate, but A is going to be quicker in getting the substrate. It has more affinity, so it will get a quicker hand of the substrate, and hence it's going to apparently show us a higher growth rate in comparison to B. Is this fine, the explanation, or if you are not convinced, you can let me know. You can explain. Okay. Be careful, like when you are repeatedly seeing this term case, mu max, and everything, you naturally tend to get confused. But even though we are exposed to a lot of questions, just be clear. Okay. So the next question is, the process engineer wants to model a large, rapidly changing shift in dissolved oxygen that causes temporary changes in the enzyme level. Which model would you suggest that he use? The answer is explicitly there in the option. Exactly. So, when we talk about changes in enzymatic level, it means it is more of intracellular component based change. Your unstructured model is going to consider your cell as a single entity, Therefore, you cannot model for the internal composition and all. So, but we want to model only the change in enzyme level. So it's not unstructured model. And Malthus model is about population size, and it on the other hand assumes the exponential growth. That also you cannot use. So the statement itself is not just the structured model. It tells that it can represent intracellular components. That your enzyme is one of the intracellular component. So it works. And simple plate count model, no, I mean both Malthus and plate count will tell about the population, but nothing, no insights on the intracellular level components. Okay, a researcher doubles the path length in a spectrophotometric measurement, but he keeps the concentration constant and remaining within the B Lambert range. Which of the following is expected? When we talk about Beer-Lambert's law, it tells that A is equal to epsilon Cl. A is the absorbance value. The absorbance value is going to be the product of your molar absorptivity. This is a constant, and it is a specific um, thing for each of the molecules that we want to analyze. And then you have the concentration, which eventually you want to find out, and then you will have the path length of the cuvette that you are using. And this path length decides the distance the light travels through the solution. It can be 1 centimeter, which is very common, or it can be of different ranges. So because the equation is A is equal to epsilon Cl, there is a direct relation, linear relationship between um, absorbance and the path length. They are directly proportional. Therefore, when the path length doubles, the absorbance value also is going to double. Okay. A high substrate experiment shows that the growth rate rises initially but falls when the substrate concentration is increased. What does this suggest? Like the first question that we saw today was similar. The assertion of the first question that we saw today. Whenever we increase the substrate, we cannot directly expect an increase in the growth rate, mu value. So this is substrate increase. Okay. Final part of session is some problems. We'll just solve some. A culture contains 0.18 gram per liter biomass at 2 hours and 1.44 gram per liter biomass at 8 hours. Assume that the culture remains in exponential growth during this interval. Now you have to calculate the specific growth rate, calculate the doubling time, and estimate the biomass at 10 hours if this exponential growth continues. It's just two equations and you are done. But you should know what equations to use. You are given with the time and the population. You have to calculate the growth rate, doubling time, and at a given time what would be the population. Always. Okay, I hope you are solving the problem, but keeping in mind the time, I will just show through the remaining problems with the questions and the answers. You can come back to these maybe in the video again. So here, yeah, right, your growth rate is right. So the first question is calculate mu. Mu is ln x2 by x1, the population divided by your T2 minus T1. Here your T2 is 8 hours and x2 is 1.44 and T1 is 2 hours and x1 is 0.18. So when you substitute, you will get 0.346 or 0.35 per hour as you mentioned. And when you talk about the doubling time, so we have seen in a lot of previous questions that doubling time is ln 2 by mu. Now you have your mu as 0.35. Ln 2 by 0.35 is going to be 2 hours. 1.98 approximated to 2 hours. Okay. And then estimated biomass at 10 hours. So xt is equal to x naught into e power mu t. You have your mu value. You know that at the end of 8 hours it was 1.44. So that you will have as x naught or the initial value here. So from 1.44, if the growth rate of 0.346 within the next 2 hours, which is the time interval is 10 minus 2, the next 2 hours, it's going to be 2.88 gram per liter. Next question is, two organisms have the following kinetic parameters at substrate concentration of 1 milligram per liter and 100 milligram per liter. Calculate the growth rate of each of the organism. Which organism is preferable under substrate scarcity and which is preferable when the substrate is abundant. So the kinetic parameters are given here. Organism A has a mu max value of 0.6 per hour, whereas B has 0.9 per hour. It has a higher value. But the Ks of A is lower, 2 milligram, which means the affinity of A is higher, whereas for B, Ks is higher, 10 milligram, so that the affinity is lower. So now at S is equal to 1 milligram per liter, the substrate concentration is very low. So the growth rate of A is going to be 0.2, whereas B is going to be 0.8 because it has very low affinity. This is the equation, mu is equal to mu max x by Ks plus S, which was used to find the mu here. But when the substrate concentration is very high, 100 milligram per liter, you see that mu A is going to have 0.588 per hour of growth rate, and B is going to have an even higher growth rate because the substrate is in excess. When the substrate is in excess, the mu max value plays a major role here. This has a higher maximum growth, specific growth rate. So it exhibits the maximum specific growth rate. It can multiply faster than A, and therefore it has a higher specific growth rate in the given condition. That's what is explained here. At low substrate concentration, A grows faster. At high substrate concentration, B grows faster, and the reason, as I had mentioned, is the affinity and the substrate availability. Next is a batch culture displays exponential growth initially, then gradually approaches a nearly constant biomass concentration. The substrate concentration is not measured and the inhibitory products are believed to be negligible. Which model is more appropriate here? Why would monad model not be the first choice based on the available data? So this we have discussed enough. We are telling that it's going having exponential growth and it's going to reach a constant biomass concentration. So when we talk about this constant biomass concentration, we obviously choose the logistic model, which tells that dx by dt is equal to mu x into 1 minus x by x max, the carrying capacity. And then why not the monad model? Because the monad model requires a substrate concentration to tell us about how the specific growth rate will be. But here we don't have the substrate data, and therefore monad model cannot be used. Next question is, a culture is inoculated at 0.25 gram per liter. It has a lag phase of 1.5 hours followed by exponential growth at mu is equal to 0.28 per hour. After 7.5 hours, what will be the biomass concentration and how much time will it take to reach 2 gram per liter? This is very simple, but one thing that you have to have in mind is your time is going to be 7.5 minus your lag phase, because in lag phase you will not have growth according to the mu that is mentioned here. In lag phase your mu is not going to be 0.28 per hour, so you should not include that 1.5 hours here. Apart from that, it's just x is equal to x naught into e power mu t, but your t is t minus t lag, the time given here minus lag, those 6 hours. Okay, and the time required again you can find out using the same in its logarithmic form. So here you will find one time, ln of x is 2 to reach 2, and your starting point is 0.25 gram per liter and your growth rate is 0.28 here. So ln x2 by x1 is equal to mu into t minus 1.5. So because it takes this time here is 1.5 hours, but when you are to solve this you will get 8.93 hours. Okay. Next question is, a culture has the following biomass concentration. Identify the likely growth regions. Estimate the specific growth rate in this first and second exponential region. Explain why the second growth rate may differ from the first. So from this you know that this is going to be some kind of a dioxic growth. Here you can see within the first 2 hours the biomass doubles from 0.1 to 0.2, and here again from 4 to 6 it remains constant, which means there is a lag phase here. So here there is an exponential growth, and here again there is a lag phase, a plateau, and again it increases, like from 0.4 to 0.8 to 0.16. So first exponential phase is this 0 to 2 sorry 0 to 4, and then here you have one more exponential phase. The lag phase here is the 4 to 6 hours, that is the lag phase. The culture shows the first exponential phase from 0 to 4. As you can see, the biomass concentration is 0.1 to 0.2 to 0.4, and the second exponential phase is 6 to 10. Here 0.4 to 0.8 to 1.6, but this 4 to 6 whatever is there, it is the second lag phase. And when you are going to calculate the mu from here, you can do this with initial final biomass concentration and the time. You will find it to be 0.347 per hour. So the rate is equal in this given data set, but the second rate may be lower because the second substrate may have a lower affinity. So ideally, when you talk about dioxic growth, you see the first exponential phase attributed to one of the substrates. Let's say when we are giving glucose and some other lactose, okay, the organism first eats glucose because the affinity of that organism to glucose is higher, the Ks value will be lower, okay, but only for that reason it is eating this substrate first and then eating the next substrate. So because of that, the rate will also be there will be a change in the specific rate also. In the given example we are not seeing, but in real time we can see that. Okay. Here a filamentous organism forms approximately spherical pellets. The pellet radius increases at a constant rate of 0.03 mm per hour. The initial radius is 0.2 mm. The density is constant. After 10 hours, how much we will have? Okay, sorry. After 10 hours, how much we will have? It's just 0.5 mm. You can just add it. Zero point 0.2 plus 10 into 0.03 mm per hour. If you add, you will get this 0.3. 0.2 plus 0.3, it's 0.5. By what factor does the pellet mass increase? Since the density is constant and pellet is spherical, mass is directly proportional to the radius cube. Okay. So when you're going to take a fraction of mass final by mass initial, it's going to be the fraction of radius initial, so radius final by radius initial, the whole cube. So you have the radius data. So divide 0.5 by 0.3 the whole cube. The mass increase is going to be by a factor of 15.625. The last question is, why might this simple model become unreliable for very large pellet? Because this model assumes constant density and radial expansion, but in reality large pellet sizes there can be diffusional limitations. Therefore the core of the pellet could experience nutrient depletion and toxic product accumulation, which cannot come out. The nutrient cannot go in, the toxic product cannot come out inside the pellet. So the density and the growth may not remain uniform here. The assumption of uniform density may not work when the pellets are becoming very large. Okay, our culture is currently at a substrate of 100 into Ks. The operator increased the substrate concentration to 200 into Ks with the growth rate approximately double. So for this, at 100 into Ks, mu by mu max will be 100 by 101. Mu is equal to mu max S by Ks plus S. Okay, S by Ks plus S. S is 100. Ks plus 100 Ks is 101 Ks. So it is 100 by 101, which is 0.99. When you talk about 200 Ks, it is S by S plus Ks. S by 200 by Ks plus 200 Ks, which is 201. And this is approximately 0.995. Adding more substrate is ineffective once the culture is already close to its mu max value. It will not double the growth rate. That is what I'm trying to tell here. Okay, the last question. Two otherwise identical chemostats have the same organism and substrate. Okay, but reactor A has a dilution factor of 0.1 per hour and B has 0.5 per hour. If both are in the steady state under ideal Monod assumptions, which reactor should have the lower residual substrate concentration? At lower dilution, steady state growth requirement mu is equal to D is lower. Okay, so from Monod kinetics, this corresponds to a lower residual substrate concentration. So A will have the lower residual substrate concentration. I hope it was clear. If there are any doubts, please let me know. Otherwise, thank you for joining in. Hoping to see you in the next session as well.